Hello everyone and welcome to the final video for Econ 366. Today we're going to continue our discussion concerning resource economics. And in addition to studying non-renewable resources like we did last week, this week we're going to dive into some of the standard renewable resource economic examples, such as those that relate to fisheries and forests. So my primary goal for this class is to introduce all of you to economically optimal methods for managing renewable resources over time. And similar to the management of non-renewable and depletable resources, we're going to introduce these topics by, first of all, covering I don't want to say naive, but the economically uninformed way for managing these resources. We're then going to introduce the intuition that economics would impart and show why that may provide a more efficient solution for resource management than an economically uninformed method. And in addition to considering both the biological and the economic rules for managing renewable resources, we're going to look at two different types of renewable resources, primarily forestries and fish. And then we're going to consider how some of these rules may be implemented in the real world. So the first application that we're going to consider is that of fishery management. And so we discussed last class how we could classify different types of resources, and obviously that first point of departure is between non-renewable and renewable. And within our renewable resources, we also wanted to consider resources which human beings may impact the natural rate of replenishment, and those which they may not. And so, solar energy is a great example of one that doesn't matter how much we harvest, it's going to be purely renewable, and it's strictly based on physical and I guess biological, primarily physical properties. So some, I guess our perception about what types of natural resources are going to be impacted by human behavior may vary over time as we learn more about the natural capacities for those resources to regenerate. And a good example of this is fisheries. And so there was a prominent English biologist in the 19th century who made a proclamation about fisheries in, I believe it was the Atlantic, and saying that, look, they are so plentiful, you can basically walk across the water on them. There's nothing that we can ever do to impact them, but clearly not the case based on what we know now. So here are just two examples of the catch rates for two commercially harvested fish. So one being Atlantic swordfish, the other one being Pacific bluefin tuna. If you remember, we discussed the bluefin tuna a couple weeks ago and showed how it was caught all throughout the Pacific, from Japan and Russia all the way over to Alaska, and how that's just a classic example of tragedy of the commons. So, you can see here that the catch rate initially increases for both of these as the intensity of fishing increases, and then the pressure that put on the reproductive capabilities of those populations eventually led to both of them decreasing significantly before the turn of the millennium, with Pacific bluefin tuna pretty much crashing. Another great example of the collapse of a fishery due to an overharvest would be that of the North Sea herring fishery, which reached a point where the catch rate was so low, the population was so low, they actually had to completely close and ban all fishing for North Sea herring from 1977 to, I think, 1983. And so with that intense management, the fishery has been able to regenerate and return back to a harvestable level. But without any policy intervention, if we were just left to free market uninterrupted devices, then this would have completely collapsed. And so to understand how we should optimally manage a renewable resource stock, which is both inherently biologically driven in terms of its regenerative capacity, but also creates economic value, we're going to need to rely on insights from both of these fields and possibly even more disciplines to form that most comprehensive management strategy. And so the process of doing this has become known as, or the field in which this is done has become known as bioeconomics. As you can guess from that name, it's a portmanteau for biology and economics. And it crucially relies on an understanding of the biological system, which is the fish population regenerative capacity, and its interaction dynamically with human behavior, as well as an understanding of the economic concept of rents and scarcity, so that we can most efficiently manage the value of fisheries and not necessarily just the population. And so this work is largely going to be traced back to Gordon in 1954, which was even preceding the tragedy of the Commons by Garrett Hardin in 1968. And so this is kind of going to be our point of departure for the first half of class today. And so the model that we're going to use to describe the bioeconomics of fishery management is the Gordon-Schaefer model, or just the Schaefer model. And so the Schaefer model is going to show the relationship between the growth of the fish population and the stock of fish. And so it's important to note here that the fish stock, how many fish there are in the fishery, is given on the horizontal axis, and the per period growth rate of that stock is given on the vertical axis. And so I really like this model because I think it's relatively intuitive, but to help you better understand it, I'm going to walk you through to this point. So you can find a very similar version of this model, I think, on page 128 or 129 of the book for this class. And really the only difference here is going to be this little area to the left of the minimum viable population. And so, like any graph on an XY plane, this is letting us know how the Y variable changes, in this case, how the growth of the population changes in response to changes in the actual stock of fish. So this is describing the dynamics of the change in the fish population from one period to a next based on how much of that fish is in the fishery at any given point in time. And so there's a couple of key points here that we want to understand. One is the carrying capacity, one is the minimum viable population, and both of these represent equilibrium or equilibria, so points at which the growth rate is zero, so meaning that the population of fish neither decreases nor increases, but one of those two is stable and the other one is unstable. And so what do we mean by that? So stable equilibrium sounds redundant, sounds like it's just saying the same thing multiple times, but it means that if we go away from this equilibrium, if we decrease the fish stock, and so we move to the left, then the growth rate of that population is positive, it's above zero. So that means the population, the stock of fish, is going to increase, and it's going to increase back to K. And so if we're a little bit to the left of K, then the fish stock will increase because it, according to this model, has a positive growth rate, and it means there's more capacity for the fish population to increase biologically, to increase naturally, that there's sufficient feed and prey for the fish to reproduce enough without having overpopulation and excess mortality. Now, if the population increases to the right of K, then we're in a situation where we have overpopulation. And yeah, we don't have this graph continued, but as you could imagine, it would continue in the same direction. So there'd be a negative growth rate there beyond K. And if we think about overpopulation, that makes sense. So the growth rate would be negative, and that would imply that more fish are dying than are being born, and so the population then shifts back to the left until we get back to the point where we're at K and there's a growth rate of 0, and that's where uninterrupted, if humans did not intervene, where the population would stand. So why isn't that the case at S? Why do we say that S is an unstable equilibrium? So it's an equilibrium because, once again, the growth rate is 0, meaning that if uninterrupted, if humans do not intervene and there's no biological or ecological shock to that population, then that population would stay at S bar. It would stay at its minimum viable population. Now, if the population increases, if we have S bar plus just a little bit more, then there's a positive growth rate. And so that means in the next time period, there's going to be more fish, and it's going to have an even higher growth rate. And that's going to keep going up until we hit this kind of inflection point where or we hit a peak of this curve where beyond that point, the growth rate is still positive, but it's increasing at a decreasing rate. And that is just because the fish are still reproducing. There's still enough food for them to reproduce, but they are extracting enough of the resources necessary for survival that they're growing at not as fast of a rate relative to their mortality rate as they were before that point. So if we increase the stock of fish just a little bit beyond S bar, then we're going to keep increasing it until we reach K. If we decrease it, then the assumption is that there aren't going to be enough fish to find each other to reproduce. And so while there will be some reproduction, the reproduction occurs at a lower rate than the mortality rate. And so eventually that population goes to 0. And so why it's stable, sorry, it's not stable, it's an equilibrium because if unperturbed, it would stay at S bar, but if it's changed in any way, then it's not going to go back to S bar. Whereas K, if the population is perturbed in some way, then the stock of fish will eventually return to K, to that carrying capacity. And so hopefully that makes sense, but now we're going to make it a little more complicated and introduce human activity into this model. So what do humans do when they interact with fisheries? They extract fish. And so we are going to be able to define a state of no change when the amount of fish stock and the catch rate remain constant across time. Or in other words, when the catch is just equal to the growth in the population. So we're going to define catch here as harvest. We use the variable h to define it. And here this f of x just means, it's going back to algebra, it's the y variable. It's how x changes, how y changes in response to x, which is given by our logistic growth formula, which we're not going to get into any sort of calculations involving the logistic growth equation. Just understand the dynamics described on the previous slide. But the point of this is that if the positive growth rate is, let's say, 5%, and we harvest 5% per time, for a time period, and those two offset each other, and the stock of fish from one time period to the next doesn't change. And we can do that sustainably and indefinitely, so long as those are the only dynamics impacting the fishery, the natural rate of growth of the fish, the net rate of growth of the fish population. So reproduction minus mortality, and the human catch rate. And as long as those two are going to be equal to each other, then we're going to have that stable population. And so we can then, we'll think of that as a sustainable yield. And we're going to further develop this concept of a sustainable yield in a couple of slides from now. But for now, just recognize that any point at which the harvest rate equals the reproduction, the net reproduction rate, a growth rate, is going to be a sustainable yield. And just so we have some of this terminology written down or in a place where you can review it, we're going to think of the fish stock as being represented by variable X that they catch, as we said in the previous slide, is going to be given by variable H representing the harvest. And that we're going to think of the stock of fish at time t being equal to the stock in the previous time period, so t minus 1. So if this is 1999, then t minus 1 is 1998. And in addition to the stock in the previous year, in the previous time period, we're going to add the growth rate of that population, so reproduction minus natural mortality, and subtract from that the harvest, or the amount taken out by human catching. And so in the equation representation of this, we have x of t equaling x of t minus 1 plus f of x, the growth rate, minus the harvest. And so you can pretty naturally see here that when f of x is equal to h, then x of t equals x of t minus 1. The amount of fish in 1999 equals the amount of fish in 1998. So relatively simple relationship that we can think about there. And so as we discussed a couple slides ago, any point along the Schaefer logistic growth curve can represent a sustainable yield so long as we set the harvest rate equal to the growth rate at that particular stock of fish. However, while we could have this considerable range of different sustainable yields, there is going to be one maximum sustainable yield, which is going to be the harvest rate, which we could sustain in perpetuity, which would be the greatest of all possible harvest rates, which we could sustain in perpetuity. And so that would be maybe our biological concept for maximizing the amount of fish which we can extract at any point in time. However, as we indicated at the beginning of class and we demonstrated in the previous week's video, there's going to be a difference between the economically uninformed optimal resource management rule and then the resource management rule, which uses some insights from economics. And so before we do this, let's make some standard assumptions. The first of which is going to be that the price of fish is going to be constant due to perfect competition. So that's clearly not always the case. But as we mentioned last week, this can be a good baseline assumption, and we can see how the model may change as we relax that assumption. We're going to set the marginal cost of a unit of fishing effort to be constant as well. And so not of a fish catch, but of the amount of effort which we exert to catch the fish. And we're going to propose that the amount of fish caught per unit of effort is going to be proportional to the stock, meaning that if there are more fish, then the same unit of effort is going to give you more catch, right? So if you just we define effort as boats or hours spent fishing, then as the population, as the fishery gets larger, then sending out that same boat is going to be able to extract more fish when there's more fish in the sea than if the fishery is relatively depleted. So with these assumptions in mind, we can then think of this problem in terms of fishing effort. So once again, that could be hours spent fishing, number of boats spent fishing, or boats used to catch fish, rather than the stock or the quantity of fish. And importantly here, that effort is going to have a cost as well as a benefit. So remember that we are still going to be looking for sustainable yields and how we can keep the fishery operational indefinitely in the future. So we can use those assumptions and the Schaefer logistic growth function to think of a relationship between harvest and effort, and that's going to give us this inverted curve, which is going to suggest that as we increase our effort fishing, initially that is going to lead to more harvest, right? You put more boats out on the water, you're going to catch more fish. Eventually, the amount of effort we spend ends up decreasing the total harvest as we overfish a given fishery, and eventually the harvest per unit of effort is going to decrease down back to zero. And so in between that initial harvest of zero when there's no boats and their harvest of zero when we've put too many boats out in the water, there's going to be a maximum level of an optimal level of effort, which will maximize the per unit, per year sustainable harvest rate. And so it's important to note that we can't directly choose how much we harvest, but we can just choose how much effort to spend fishing. And so just to reiterate what I was saying previously, fishing effort can be described in many ways. We could think of it as being the number of vessels, number of boats, the number of trips. So not just the number of vessels, but the amount of trips that each of those boats are taking, the amount of days spent fishing. So not all trips are going to be of the same length. The amount of expenditure on the fishing power. So being the amount of crew on the boats, the type of gear that they're using, or any combination of all of these above. And so when we want to calculate the optimal amount of effort to spend fishing, we want to think about, once again, maximizing our net benefits in perpetuity. And so for now, we're going to ignore discounting, ignore the our time preference when we're making these calculations, or not calculations, but graphically demonstrating where these points would be. And we're going to remember that the total benefits are going to be equal to the price multiplied by the catch. And so if you're selling halibut for $20 a pound and you get 1 million pounds of halibut, then you're selling, your total benefit is going to be $20 million. So if we then remember that the catch per unit of effort is going to be proportional to the stock of the fish, which is reflected in the inverted shape of the yield to effort curve there, and we consider that the total costs are going to be increasing, then we can have a pretty clear picture of what the relationship between the costs and benefits will be, and we can determine what our optimal level of effort will be. And so just like in a supply and demand graph where our demand is our marginal benefit and our supply is our marginal cost, we want to pick the area which choose the allocation which is going to maximize our net benefits, or the difference between our total benefits and our total costs. And so when we make that selection in this model with fisheries, we are going to choose the optimal level of effort, which is going to maximize the difference between the green total benefits curve and the red total cost curve. And so while the economically uninformed rule for maximizing the catch rate over time is setting your harvest equal to that maximum sustainable yield at the peak of the Schaefer growth curve, or which will be proportional to the total benefits curve here, that's not going to take into account the actual cost of fishing. And so when we include increasing total costs as the amount of effort that we expend increases, then we're going to see that efficient level of fishing effort is going to fall to the left of the level of effort which would set us equal to the maximum sustainable yield. In other words, we're going to attempt to extract less fish than would be the amount of fish extracted, which would be the maximum sustainable yield. And so now that we know what the efficient level of effort or harvest would be when we can completely manage the catch rate throughout the fishery, let's consider what would happen under open access. So what would happen when there's no management of the fishery and everybody's free to extract as many fish as they want. So what we're going to consider now is just a completely free market where we're going to have different actors all going after the same benefits and incurring the same costs, but we're just going to have a misalignment of incentives between what's best for the entire fishery and what's best for the individual. And so the table that I have presented here is a way to introduce the tragedy of the commons that is going to be the product of what happens when there is that misalignment of incentives. And so this table is just going to demonstrate a very standard supply and demand graph where we're going to have a quantity on the horizontal axis, and we're going to have benefits and costs on the vertical axis, typically thought of with price, but in this case we can just think of it as a catch rate, which would then, like if we just assume a price of $1, then we can just assume that the catch is going to be also the dollar equivalent. And so the marginal cost curve, the supply curve, is just going to be flat. It's going to be constant at 2. And so the two columns I want us to look at first here are total benefits and total costs. And so if each unit of effort is going to have a marginal cost of 2, constant marginal cost, then that marginal cost obviously is going to be fixed at 2. The average cost is going to be fixed at 2 because the first unit of effort requires 2 units, it costs 2 units. The second unit of effort costs 2 units. And so that average is going to be the same as the marginal, and the total cost of 7 units of effort is going to be 14. Now, on the benefit side, let's assume that the first unit of effort is going to lead to 8 fish being extracted. And so the average benefit then for that 1 unit of effort is going to be 8 fish. The marginal benefit from that first unit of effort is going to be 8 fish. When the second fish is extracted, we're going to have decreasing marginal benefits. Remember, marginal benefit is a demand curve. There's typically going to be the law of demand suggests that the marginal benefit is going to decrease as our quantity increases. And so the marginal benefit is going to decrease from 8 to 6 here, meaning that we add 6 to the total benefit from the previous time of 8, and we have a total benefit of the second 2 units of effort being 14 fish. Well, we divide 14 by 2 to get the average benefit, and that's 7. We do the same thing for effort level 3, 4, 5, 6, 7. And so you can see that the marginal benefit curve decreases pretty steeply, but the average benefit curve decreases less steeply, right? So when there's a marginal benefit of 4, meaning that the total benefit that would be 4 plus 14, and it's 18, we divide 18 by 3, the average benefit is 6. And so there's a couple key points here that are important to note. One would be when the total benefit equals the total cost, in which case we have the open access arrangement, and we'll demonstrate why that's the case in a second. And then we also have our economically efficient level of effort, which is when the marginal cost of 2 is going to equal the marginal benefit. And so we know from supply and demand that's going to give us our point at which is going to maximize our total economic surplus. And so that would suggest that the efficient level of effort to exert here is going to be 4 units of effort, which the marginal benefit of that 4th unit of effort is going to equal the marginal cost. However, the open access problem lies in the individuals taking advantage of the commons, not thinking about what is in the marginal benefit of society, but what's in the marginal benefit for themselves. And so if we, instead of thinking of these units of effort of being hours spent fishing, but number of boats, then you could see that once again, for that first boat on the water, they're going to get 8 fish. Second boat on the water, though 14 fish are extracted, each boat is now only getting 7. There's some competition. And so there is a positive incentive for more boats to go into the fishery, as long as the benefit that each boat can expect to get is greater than or equal to the cost that they're going to spend. And so since the average cost here is $2, or it is 2, and the average benefit is 2, then there is a signal for profit right up until the point that the total benefits from extracting the fish equals the total cost, which is going to result in far more fish being extracted than would be the case if we thought of the economically optimal way to solve this. So I'm going to demonstrate the same information graphically now instead of just in tabular form. And so feel free to rewind the video back to that previous table if you need to do so. And just keep in mind here that this first point on the far left of the x-axis should be 1, not 0, for the math to work here. And so the relationship between marginal benefit and average benefit that we described in the previous table obviously holds here. Average benefits decrease at a slower rate than marginal benefits do. And eventually we hit a point for the level of efforts, or in this case, quantity, that the marginal benefit quickly becomes below 0. And so not only is it below the marginal cost, but for that 6th and 7th unit of effort, there's going to be a negative marginal benefit. And we're actually decreasing the total benefits by overfishing. And so that is unfortunately going to be the case when there is just unadulterated open access to the commons. And so this Q star here is going to represent our efficient level of effort or management of the resource in the Q open access. Obviously, being greater than the Q star is going to represent what would happen when we don't have any sort of system governing the commons. And so if the tragedy of the commons due to that misalignment of social incentives versus private incentives resulting from open access to a common resource is defined by the point where total cost equals total benefits, it's pretty clear to see out of points A, B, C, and D where the open access level of effort would be on this graph. And it is at that point C where our total cost curve intersects our total benefit curve. And so we can see that not only is that to the right of point A, which is our maximum economic yield, the sustainable level of effort, which is going to maximize the value of our annual catch in perpetuity, but it's greater even than the maximum sustainable yield of B, being that maximum amount of fish that we can catch in perpetuity. And in fact, point C is defined by no profit. And so it's clearly going to be an inefficient solution for the fishery. And so we could define that open access equilibrium where total cost equals total revenue, and total revenue just being the economic equivalent here of the total benefit. And so total cost is just our per unit marginal cost multiplied by the units of effort which we spend. And we would set that equal to the total revenue, which is just going to be price times yield. And if we're assuming that the price is going to be proportional, then the yield is given to us by the harvest, which is equal to a catchability coefficient, which is going to change with regard to the stock, the level of effort which we're spending, and the level of the stock. And so once again, you're not going to need to calculate any of these, but that's more or less how we get set about solving for the open access equilibrium level of effort. And so the economic interpretation of why that open access equilibrium is inefficient could be that while there is a market for the fish themselves and a price for the fish, there's not a market for the scarcity of the fish. We're not taking into account the marginal user cost for the increased scarcity that we're imposing in the future by extracting more fish today. And so just to return to some of the management strategies for the commons that we considered a couple weeks ago, we can use command and control approaches, we can use market-based instruments, we can try to create property rights, so that's obviously challenging in open waters, or use collective management as suggested and recommended by Nobel Prize winner Elinor Ostrom. Though I once again should be specific, when you win a prize, Nobel Prize in economics, it's not a real Nobel Prize, it's the Memorial Prize in memory of Alfred Nobel, because he didn't actually leave money for economics, and economics just kind of wanted to be taken seriously, so we created our own and gave it a name to suggest that it's a real Nobel Prize. So some examples of command and control approaches for managing the commons with regards to fishing would be vessel and gear restrictions, being what type of net you can use. Can you use a net at all, or do you have to use line fishing, for example, for tuna? What is the length of the boat? Imposing time restrictions, so being maybe the number of days which you can spend fishing, setting time months in advance for when the fishing season would open and when it would close, setting the length of the fishing season, allowing a total allowable catch, so no fishing after you've caught your maximum permitted level of number of fish, or making spatial restrictions to allow populations to breed and recover, specifically in areas which are important, like what are nurseries for fish. And so because this is economics, we should probably be aware that when we impose a command and control approach, it's going to change the incentives for the individuals in that market, and that individuals respond to incentives. And so one example of a command and control approach being shortening the duration of the fishing season provides the incentives for captains of fishing fleets or commercial fishers to just increase the number of vessels, number of boats out on the water during that season. And so that's actually what was observed to be the case in an Alaskan fishery between 1984 and 1994. Season length was decreased to protect the stock of the fish, and the fishers just responded by increasing the number of boats out on the water. So there's a really great podcast, which I'm going to link to in the comments for this video. You're not required to listen to it, but if it's of interest to you, by all means, I'd recommend it. It is from the same NPR Planet Money podcast that we listened to in the previous week, but they note that one of the other side effects, one of the other unintended consequences of a command and control approach of setting the fishing season months in advance and having it be shorter was that regardless of what the weather was, the marginal benefit of going out fishing on a given day was going to be increased because you wouldn't have the capability to go fishing on another day. And so even though the marginal cost was higher due to worse weather, potentially because these dates were set months in advance, the marginal benefit to the fishers would be such that they'd go out in the bad weather. And that's what led to the conditions for the deadliest catch and what led to crab fishing and other types of fishing in Alaska to be such dangerous careers. In the list of unintended consequences of command and control policies goes on. So vessel and gear restrictions are going to be inefficient due to the increased cost of those boat length and types of nets. The time restrictions lead to more vessels, better gear, ways of, or better, more expensive gear, more dangerous fishing conditions. Setting a total allowable catch is going to lead to the fish being depleted sooner, and establishing protected areas may lead to more fishing in the non-protected areas. However, they may be efficient in the same way that a Pigouvian tax is efficient in shifting the equilibrium to the left and up in a supply and demand graph, decreasing the equilibrium quantity, increasing the per unit cost. Similarly here, if we have the cost curve TC1 representing the total cost in an unregulated fishery, and then we impose gear restrictions, vessel restrictions, which increase the per unit costs and lead to total cost curve 2, then we can shift the equilibrium level of effort to the left of the maximum sustainable yield, perhaps closer to what the maximum economic yield would be. And so while it may be, while such regulations may be inefficient, if the market is already in the optimal equilibrium, if we are in a world where we have that open access depletion of the resources and fishing to zero profits, then it may be still efficient as a way to get to that maximum economic yield. And perhaps the best way to do this is going to be through market incentives. So as we've indicated in the past, when we just impose a command and control restriction on quantity, or we impose that all firms have to abate the same amount, we're going to leave room for improvements through trade. And one way that we can do that with fishing is through individual transferable quotas, similar to tradable permits in markets for pollution abatement. And so really these would operate almost the exact same way, and allows for us to kind of combine the command and control quantity approach with still ability for the market to capitalize on different levels of efficiency across market participants. We can also impose taxes, which will raise the cost of fishing, similar to what we were just illustrating on the previous slide. But in this case, instead of imposing potentially wasteful spending, the surplus, the amount that is going to be spent, can be sent back to the government and perhaps used to pay for methods to regenerate the stock of the fish. So to pay for the protection of marine environments, or other methods for maybe paying for artificial nurseries as a way to increase the stock of the fish. An alternative solution, when possible, may be through aquaculture. As we indicated with the tragedy of the commons, the problem there wasn't the shape of the demand curve or the marginal cost curve. It was due to that misalignment of incentives from a common good, where the good is rivalrous but not excludable. And when, if we can make the good excludable, then there's more of an incentive to sustainably manage your own portion of the stock. And so one way that we can do that with fishing is to allow for the farming of fish rather than just open water access catching of the fish. And in fact, over the past 50 years, we've seen the percent of fish on the market which were raised via farming rather than provided via open water capture increase from less than 4% to over 40%. So, an order of magnitude difference there. And that has significant benefit in terms of the management of open water fisheries, but also is going to potentially come with some costs as well. And so the externalities imposed by aquaculture can occur at the local level. They can occur at the regional or like coastal wide level, and can even occur at the global level. And it may lead to eutrophication or too much nutrient loading in local waterways due to either the fish waste or the food which is needed for the fish. It may lead to impacts on native fish populations if some of the farmed fish escape. And globally, this could also provide the incentive for greater fishing for the prey fish, which are needed to sustain the farmed fish, which may then lead to ramifications throughout the marine food webs. All right, so for the rest of class today, and really for the rest of the videos for this term, I want to spend discussing the economics of forestry management. And so forests are really a unique natural resource, and that they provide a variety of benefits in terms of their instrumental value to us as humans. They support biodiversity, they provide timber as an extractable good, and also provide ecosystem services in the form of potentially flood risk management as well. There we go. So over time, obviously, there's been global deforestation. These maps are a little bit old, 10 years old now, but the general point is, the general trend is still going to hold. So if we look at the original forest cover throughout the world, obviously we can see that there's a significant portion of the global landscape which was originally covered with forests, in addition to obviously large areas of deserts, as well as more mountainous areas. And over time, that's changed. And so while the area where you can find the forest is largely the same, and I'm going to recommend jumping back and forth in the video to compare these two graphs, but specifically look at India on the previous slide and then look at it now, look at other parts of Australia and some of the islands between those two areas. And while we still do have qualitatively similar areas of forest in the Western Hemisphere, obviously deforestation of the Amazon rainforest has been a big part of forest loss throughout the world. And so where did that original forest landscape go? What did it do? Well, some of it became cropland, and specifically that's what we see throughout India and throughout parts of the Midwest and the US and throughout a lot of Europe, as well as eastern Brazil. Some of it is now pasture. Once again, also in Brazil, that you can't see that as much, a lot in Latin America and parts of Australia. And we can further break down the existing forest cover into intact forest landscapes and working forest landscapes. So these working forest landscapes are going to be rotatable, meaning that they're going to be managed in a way that we will let the forest stock grow and then we'll harvest it for timber and let it grow again. And so deforestation does have significant benefits. That's ignorant of us to assume that there isn't a benefit of converting forest land to cropland or pasture land. That's not to say that the costs don't outweigh the benefits, but global hunger is a problem, access to food is a problem, and being able to provide more food to a significantly growing population, such as India over the past 100 years, has been a way that has prevented, I won't say needless suffering, but has prevented more people from dying of starvation than actually did die of starvation, which is still sizable. However, there are obvious externalities involved with deforestation, and globally, deforestation and forest degradation account for 20% of net global greenhouse gas emissions, which is more than the entire transportation sector. And so when especially we take into account the role of agriculture and deforestation, that's a sizable part of our climate change contributions. And so while we can certainly study the economics of the conversion of forest land to cropland or pasture, we're going to spend the rest of this class thinking about the economics of the management of those working forests, of the rotation, of the harvest of timber from one time period to another. And so, as indicated earlier in our discussion of our introduction to forestries, timber is unique in many ways. It's both an output of what is harvested, what is sold, as well as a capital good in it gaining in value. Once again, think of natural resources as leaving it in a bank and having it gain value over time. So the decisions regarding the management of timber are going to not just be one-dimensional in terms of how much effort to spend, but are going to involve decisions about how much timber to harvest, how often to harvest it, and whether to replant it after harvesting. And there are considerable positive externalities from the existence of those timber stands, as well as negative externalities from harvesting the timber itself. And so just like fishery management, there is a biological component to forestry management and an economic component as well. And so first, to focus on the biological component, we're going to consider tree growth as being measured on a volume basis, similar to fish being managed in weights or tons. We're thinking of not only the number of trees or the height of the trees, but the total volume of the timber. So considering the diameter of the trees in addition to the height and the actual number of trees. And so young trees will grow tall very quickly, but the volume growth is slow. And then by the time they reach their medium age, then they start to expand more rapidly in terms of their circumference and diameter. And then the mature trees level off in terms of their growth, and they grow very slowly, eventually stop growing. And also, the longer the trees exist, the greater the likelihood they're going to be affected by the weather, the soil fertility, disease, forest fires, etc. And so those all impact the average volume of a timber stand throughout the years. And so if we were to take an economically uninformed approach to maximizing the amount of the harvest that we can extract from a timber stand sustainably over time, then we would want to think about finding the mean annual increment, which is going to be the volume of the trees at time t divided by the number of years at which that volume is calculated. And so that mean annual increment will be maximized when the marginal growth rate at age t is equal to the average annual growth rate. And so this is going to be more intuitive to visualize when we can see the graph here. So once again, the mean annual increments, the volume of the trees at age t divided by the number of years in that age. And we think of that mean annual increment as being maximized when the average growth rate is going to be equal to the marginal growth rate. So for those of you who have taken calculus, either at the high school level or here at K, you know that the marginal change in the stock of the volume of the timber here is going to be given by the tangent to this curve at any given point. And so the marginal change in the growth of the timber at when it's 20 years old is going to be relatively low. It increases when it's 60 years old. It's pretty steep, growing pretty rapidly, and then starts to level off again as it ages due to the biological reasons which we mentioned earlier. And so importantly here, if we wanted to calculate what the average growth rate would be for any number of years, we would just draw a line from 0, which would connect to that point. And so we can visually determine what the point at which the marginal growth rate would be equal to the average growth rate by drawing a line from the origin from 0, 0, so that it is just tangent to the growth curve for the timber stock. And so that is going to set the tangent line, which is the marginal growth rate at that number of years, equal to the average growth rate. And so in this case, the mean annual increment is maximized if the forest stand is harvested every 80 years. So this means that the amount of timber in terms of volume, which we can expect on an annual basis, is going to be its greatest if we let a timber stand grow unperturbed for 80 years, harvest it, and then replant it. However, that is purely the biologically optimal rule for managing the maximum amount of timber which could be harvested on an annual average basis. There is no conception of costs or time preference in that rule. And so when we want to introduce economics into that decision, let's say that we're starting out with a clear field with nothing planted. Our objective then is to determine what the optimal rotation length, how frequently we should harvest any timber which we're going to plant on that land would be. And so the rotation length will occur when the present value of the net benefits is going to be maximized. So thinking of converting future value to present value here with a time preference, and not just thinking of the total benefits, but of the net benefits, so subtracting out the costs. And so the benefits are going to be measured using the potential volume of wood given the growth rate and the price of lumber. And the annual incremental growth is going to represent the marginal growth. The planting costs are going to be immediate, and thus they are not discounted, while harvesting costs are going to be discounted because they're occurring in the future. And so the net benefits are going to be calculated by subtracting the present value of the costs from the value of the timber at its harvest age. And obviously then we're going to need a discount rate to calculate what that optimal harvest decision would be. So just like we did last week, let's consider what the intuition would be of introducing a discount rate into this decision. So holding all else equal, if the discount rate increases, what would happen to the optimal rotation length? In other words, how long to let the trees grow? So if the discount rate increases, are we going to increase that optimal rotation length? Are we going to decrease it, or is it going to be unaffected? So you should have the first guess here that it's not going to stay the same, that once we introduce time preference, if we have a decision which has a temporal component to it, it's going to change. And so taking into account that the value that you're going to get from harvesting the timber is going to occur in the future, if we are more heavily discounting the future, then that value is going to decrease. And so we want to bring that harvest closer to the present, and it's going to lead to a more frequent rotation of the timber, more frequent harvesting with a shorter period of letting the timber grow. So to start considering some equations and economically informed rules for the optimal management of forest stands, let's start off with some basic assumptions. And so we're going to assume that the price of timber per unit of volume per cubic meter is going to be constant, that we consider this to be a perfectly competitive market, and that the production decisions by one particular firm or forest stand aren't going to impact the market price. We're going to assume that the marginal cost of harvesting per cubic meter are also going to be constant, and that there are fixed costs of planting the forest, which are going to be incurred at time zero, meaning at the present time, so we don't discount it. So given all of that, what equation should we use to determine what the optimal time or age should be at which the timber stand should be cut in order to maximize the present value of the net benefits? So before we explore that equation, let's just reiterate some of these key terms that we're going to need to consider, one of which being the harvesting costs, and that considering that they are discounted or proportional to the amount of timber harvested. So the per unit harvest costs are going to be constant, but the total harvesting costs are going to increase as the amount of timber harvested increases. The net benefits of a unit of wood harvested at any age is going to be the price of that wood minus the marginal cost of that particular unit of harvest. Tax levied on each cubic foot of wood harvested would simply raise the marginal cost by the amount of that tax, and both high discounting rates and high replanting costs could make replanting prohibitively expensive, suggesting that you would just harvest the timber and then not replant anything at all. And so there are, once again, significant varieties to this type of problem, and we'll consider even more. And I'm not going to ask you to calculate this, but basically just to understand the intuition behind the model and to be able to qualitatively reason your way through what the predictions would be. So just like in a supply and demand framework where we find what that optimal quantity would be Q star, or in a fishery model where we find the optimal level of effort, which is going to maximize net benefits, in this case, we're going to find the optimal rotation time, the optimal time to harvest the entire stand, which is going to maximize the present value of the net benefits. And so remember, when we convert present value to future value, or future value to present value, we just divide the future value. So the price per unit of wood multiplied by the units of wood, divided by the 1 plus the discount rate raised to the number of years in the future. And in this case, that's actually what we are selecting. We're selecting that exponent. And so if we place this, if we insert variables for what these actual terms are, we have P multiplied by Q of T, because the volume of the wood is a function of the number of years in which we let it grow, divided by 1 plus R raised to the T. And then we also have the present value of the costs, which are going to be those fixed costs which are not discounted, plus the present value of the harvest cost. So once again, the future value of the harvest cost being the per unit cost, the marginal cost for a unit of timber, multiplied by the quantity of timber which exists at time t, it's a function of time, divided by 1 plus the discount rate raised to the number of years which we select to let pass before we harvest the wood. And so we subtract then the present value cost from the present value benefits, and we find a T star that maximizes this whole equation. And so that looks daunting. But at the end of the day, this is just finding the first derivative of an equation. It's just, calculus math 112 here at K. So calculus is not required for this class. I'm not going to ask you to make any sorts of calculations. I just want you to know that were you to attempt to calculate some of these equations and find that optimal rotation period T, all it is taking that equation, taking the first derivative, setting it equal to 0, and solving for T. So this isn't extraordinarily challenging math. And so the principles which we can keep in mind, which will impact this decision, are going to look somewhat similar to those which dictate the optimal strategies for extracting a non-renewable or depletable resource, except now there is a regeneration rate for this resource. And so the forestry model kind of looks like a combination of the non-renewable resource model and the fishery model, which we've considered so far. And so the forestry model is going to be similarly defined by a no arbitrage condition, in that we can do a couple of things with our forest stand. That we can either cut the timber now and put the money in a bank, or we can keep the stand of timber. But that optimally what we should do is maintain the stand of trees as long as the stumpage value, the option value of harvesting at a future point in time due to the increased value from increased growth, is growing faster than the rate of interest, and then harvest it and collect the payment from selling the timber and shift your assets, which were trees, which were converted into capital, into a bank, and let that account then grow at an interest rate which is greater than the stumpage value is growing. And so we can further complicate the problem by thinking of different planning horizons. And first we can consider an infinite planning model, which is going to be different from the single harvest model, which was just what is the time at which you want to harvest the trees without replanting. But now we're going to assume that we're going to harvest the trees, replant it, and then follow that same pattern indefinitely. And this is then going to involve some interdependencies between the periods. So decisions to delay harvest for a particular rotation are going to impose costs on the next harvest period. And for this case, the opportunity cost, or what we're giving up to get more of something else, of delaying the next rotation must be outweighed by the gain in the tree growth. So we're discounting the future. We're placing the revenue from selling the timber even further into the future, which we are decreasing the value. We need to weigh that against the increase in volume from letting the tree grow a little longer. And so, holding all else equal, the optimal rotation in the infinite planning case is going to be shorter than the single harvest case, in large part because of that opportunity cost of delaying the revenue from the next rotation. And so basically this is going to enter into the equation through an increased marginal cost of delaying the growth of timber. And so just like with fisheries, we're not trying to maximize the total volume or weight of the harvest. We're trying to maximize the net present benefits, taking into account the cost of planting, the cost of harvesting, and the discount for the harvest costs and for the profits from selling the harvest. And so there's some really cool programs which you can run, which would find that optimal duration, that optimal T star for harvesting your timber crop over an infinite planning horizon based on assumptions about a discount rate, about the per unit costs, about the price of wood. And you can essentially wind up with a graph which looks like this, which shows as time passes what happens to the volume of your stock, and then eventually hits a point where you cut it down and you start over, let it grow again. And so this still follows that logistic growth equation, which is going to kind of have like that S shape to it. It's just so stretched out, so elongated that it kind of looks more linear. But basically the same rule from fisheries applies here. We don't just want the economically uninformed maximization of the volume or weight. We want to think about maximizing the net present benefits. And so you'll notice so far when discussing our costs, we're really only mentioning harvest costs and planting costs. We haven't discussed any of the externalities of logging or timber harvest. And there are considerable externalities. So one is that we could lose ecosystem services, that there's homes for, well, I guess I'm jumping ahead to loss of biodiversity, but there are homes for owls, birds, mammals, insects as well that we're losing when we harvest timber, that they may provide stability for the soil, prevent erosion. They may increase the fertility of the land, and obviously they're capturing carbon as well, and so may accelerate climate change. So all of these are costs which are, or depending on how we formulate them, benefits of letting the forest, the timber stocks remain in sight, that we could consider, we could introduce into that optimal rotation model. And just to give you an idea of what some of these more comprehensive models look like, the Faustman model is going to also consider an infinite number of rotations and is also going to assume that soil fertility, real prices, costs remain constant over time, but is going to take into account the future land value when making the decision about the optimal rotation period or the optimal harvest age of the stock of timber. The Hartman model then adds further complexity and further realism by introducing the amenity values of wildlife habitat, erosion control, water cycle maintenance, basically the positive externalities from standing timber. And so, as with any natural resource or environmental amenity, there's going to be a strong connection between the decisions which the individuals make, which impact those amenities or resources, and the incentives which government policy creates. And so government resettlement programs across the world have heavily encouraged deforestation by facilitating the movement of people into agriculture and converting the forest land, which provides little personal benefit to them, though it provides the social benefit and the positive externalities, into cropland or pasture, as well as creating concession agreements which allow for public forests to be harvested for a cost. And there is a complex relationship between poverty and deforestation, both at the micro level and at the macro level, at a countrywide aggregate level. And within a country, within smaller areas, unowned or publicly owned forests are sometimes seen as means of providing land to impoverished people and provide them the ability to clear that land, settle it, and use it as pasture or cropland to provide a living for themselves, while obviously then imposing a negative externality on the rest of the community by eliminating that carbon sequestration abilities of the forest, as well as any ecosystem services that could provide. And at the national level, having larger debts in many developing countries where a lot of forest land is located then encourages the overexploitation of resources in order to raise revenue to pay off the debts. And so once again, there is this divergence of the incentives when we consider the negative externalities of deforestation. So what can we do collectively to incentivize the protection of forests and prevent deforestation? Well, on a country to country level, we can provide debt for nature swaps. And so this is an interesting policy tool which the US has provided in the past to other countries with that owed debt to the US but had significant forests which were being cleared as a way to raise revenue in that country. And so a country or a non-governmental organization may purchase developing country debt typically at a discounted rate if the repayment by the developing country is unlikely. And then they can trade that debt back to the developing country in exchange for environmental actions such as protection of the tropical forest. I could actually include a link to a video about this as well in the comment section of this video, so you can get further evidence of what a debt for nature swap actually looks like. We also could create extractive reserves and reserve forest land for indigenous peoples to engage in traditional hunting and gathering activities. We could create conservation easements, being legal agreements between landowners and land trusts of a government agency, which can be then sold or donated as a way to protect forested land. We could pay for the protection of forested land through UNESCO's World Heritage Fund, through international agreements which provide payments for ecosystem services such as REDD or REDD+, which then takes into account the reduced emissions through deforestation and forest degradation as providing value to the rest of the world. Or we could go full-on capitalist and take a privatized approach to the payment for these positive externalities. And one form of that is through royalty payments, which will grant payments to biologically rich countries for all products which may be developed in the future from species in those countries. And so these royalties then are incentives for countries to preserve their biological diversity due to potential developments which may occur in the future within those countries. And so in the past, pharmaceutical companies have been making payments based on shared profits directly to some of these countries, specifically large pharmaceutical companies such as Merck, or I always forget if this is InBio or InBio, providing payments to Costa Rica for any pharmaceuticals they could develop from their biodiversity. Similarly, there used to be, I believe it's gone now, there used to be the Chicago Climate Exchange, at which carbon sequestration credits could be traded on an open market as a way to account for the positive value which is attributable to the carbon absorption capabilities of forests which may be privately owned. So if you're keeping an eye on the length of this video, notice that we went a little bit over today. We've gone a little bit under in the past. So obviously we could have multiple more weeks of this class, which would go into the economics of forestry management. But I really want to tie up this video and this module in this class by returning to the key resource economics questions, which we were discussing in last week's video, which are thinking about both the efficiency of management decisions of natural resources over time, as well as predictions about the duration of the stocks of those resources in the future. And so thinking about this first question, you probably guessed what the answer to this would have been before watching any of the past couple of videos. But if we think about whether the private incentives to exploit natural resources align with the social well-being, clearly they're not going to, whether that is due to open access to fisheries leading to tragedy of the commons and fishery collapse, or whether we're thinking of the failure to account for negative externalities of deforestation. Clearly we are going to need greater management, either through a centralized government or through strong social norms and collective decision-making within communities. As for the second question, how should resources be allocated over time? We need to take into account not only the biological management of these renewable resources, but also consider the role of time preference and discounting, as well as the costs of extracting these resources over time, both for renewable as well as the cost of extracting non-renewable resources, and the I guess externality of scarcity and driving the price up in the future as well for those non-renewable resources. When we think about the third question, how might we expect natural resource prices to change in the future? Well, we need to consider a variety of factors. First of all, whether that is a renewable or non-renewable resource. If it's non-renewable, what substitutable capabilities do we have? Is there a backstop technology? Are we going to be able to transition to a renewable substitute at some point in time in the future? Is the marginal cost going to remain constant, or is the marginal extraction cost going to increase, at which point the marginal user cost decreases? And when we think about renewable resources, how are we managing them? Are we do we have a sustainable yield? Are we, if we're fishing, are we overfishing and driving a population to its minimum sustainable capacity, or are we at its maximum sustainable capacity? And a similar disclaimer would apply to the fourth question: are we running out of natural resources? Well, for renewable resources, that's going to be a question which is most often going to involve our understanding of our human involvement in the management of those resources, and looking at the complete depletion of forest land in India and other parts of the world. We need to consider the spatial scale to this question as well. Certainly it's possible within certain areas to fully deplete a natural resource. It's possible to do that globally as well, though we don't seem to be reaching that point in terms of global force, in part because there is that value to maintaining those working forests. We actually, when I was in graduate school at Ohio State, had the sustainability coordinator for, I always need to try to remember what the company was, but it was one of the largest paper producers in the US and Canada. And they said, look, nobody has a greater incentive to not deforest than we do. Like, everybody thinks of paper companies or the firms which own the timber rights as leading to deforestation, but when you compare them to private landowners or real estate developers or farmers who are going to clear that land and never convert it back to timber, it's in the long run profit interest of the timber producers to replant those crops over time. And so we need to think about the private incentives as well as the societal incentives, and realize that when it comes to non-renewable resources, oftentimes we're not going to fully deplete those resources. The price is going to increase until we hit a choke price, in which we're no longer going to extract any of that resource, and we're going to transition, we're going to hit a switch point and transition to a renewable alternative. And the question about how much of our resource endowment we should leave for future generations is intrinsically tied to what we think our discount rate is. And as you know, at this point in the term, that is a philosophical question as well as a psychological one. So a lot of this is up to your own personal beliefs, as well as what your source of ethics and morality is in life, to go back to the very first day of class. But hopefully at this point in the term, you've at least developed some understanding of the economic principles which lead to the most efficient paths for reaching your version of the good and of rights in the world on a material level as it relates to the environment, as well as understanding some key vocabulary, which is important for understanding these principles as well. All right, well, that wraps up the videos for the direct instructional content for Econ 366 for this semester. Thank you for your attention to these videos over the course of the term. And as always, if you have any questions, please feel free to reach out directly to me. Otherwise, I look forward to seeing the presentations next week, and have a good weekend, and we'll see you as the presentations get going.